So first we establish that IC is, in this case, is limited or control. Another way of think about it is that controlled by diffusion. Diffusion force in base, minority diffusion in base. So because electrons are, so I should say electron diffusion. So anytime you want to establish this current, you look at diffusion current equation. So diffusion current equation for Jn diffusion will be Q dn dx. Okay? So if you look at the equation itself, there's no constants. The only thing we need to establish is this, right? dn dx. So it's simply the slope. So because the base is very narrow in most cases, we're assuming that you will then create a constant slope. The constant slope is defined by the 2 points and the distance. So let's try to write down the equation. So this is dn. And we know that the distance between the 2 points is WB. Let's triangle again. Let me draw the figure. So if this is x equals to 0, this is x equals to WB approximately. And this will be NP at x equals to 0. This is NP at x equals to WB, right? So if you want to establish the slope, this will be NP 0 minus NP at WB. Okay? So we already know, sorry, I'm going the wrong direction. There's a minus sign, so I should start with the NP-WB, following the slope. So WB, that's the slope, minus by NP at 0. This is definition of gradients, dn dx, I should say. Assuming that it's a constant, therefore, we're going to continue our, this is Q dn. This is WB. Remember, what is NP at WB? Reverse bias p-n junction will pull it down, so it will be close to what? Give me a number. Just give a number. 0, correct. Just be brave. It's louder. So it's 0, close to 0, because it's already very low, and then we'll pull it down further. And the other side is 4 bias, therefore, remember 4 bias equation, law of junction, tell us that it should be start with the NP0 and rise by exponential VBE. Okay? So let me emphasize, VBE is the 4 bias voltage on junction 2, right? Junction, the B junction, which is junction 2 in our figure. Okay, you 4 bias junction 2, you reverse by junction 1. So then we can actually get an equation. So this would then be Q dn WB. And there will be a minus sign. The reason for the minus sign is because the current is flowing, electrons going this direction, current is going to that direction. Therefore, the minus sign is simply because it's minus x. So this will be NP0 exponential VB. So we don't actually need to mind the minus sign. If I'm defining the current, if I'm defining current going down to collector as positive, then my collector current will simply, they will get rid of the minus sign because the direction. So electrons going in that direction. Let me highlight again. So electron diffuse from emitter to collector is the main collector current. Electron going to that direction, current is going downwards. Therefore, collector current is positive. Okay? So let me follow this. This will be QDN, WB. And MP0 is actually Ni squared divided by NB. Okay? And then we have the exponential thing. So if you look at the equation, it's somewhat familiar. So this is your 4-bias p-n junction equation. The only difference is that instead of having a diffusion length, we have a finite diffusion distance, right? And then you, exponentially depending on the 4-bias diode voltage. Right? So typically we will lump all these device structures, we'll lump it, because these are all defined by device structures, or device parameters. Therefore, this will then be turned into IS exponential. You only keep the ones that depends on external voltage. So this will be my, this is the device parameter, similar to that for a diode, IS for BJT. If I'm using exponential model, then IS, I will give you the bipolar junction transistors IS. Okay? Another thing I want to highlight is, what color do I use? Sure. Oh, yeah, sorry. Okay, yeah, you're right. There's something missing. So IC equals to, this is J, I should write it down this. IC equals to Jn, there's a minus sign times cross-sectional area. What is the cross-sectional area? Remember from last lecture. Go back to your notes. What defines its cross-sectional area? In a layout, remember, what is it? What defines the, for a diode, it's pretty easy because you have only one junction. But we have two junctions, so which one defines my cross-sectional area? Remember? What should I put in? The area of emitter or collector or base. Emitter, correct? So it's AE. This is emitter area. Because the emitter defined your actually active area. So I'm adding, so then I'm lumping. I need to lump this in, sorry. Okay? Somewhat missing. So one of the very interesting results I want to highlight is that if you look at the IS, which defines the collector current, let me write it down. Q, you can do this. Ni squared. Let me rearrange it. Should be Q Ni squared Dn. I don't know where should I place my AE. These are the parameters which let me highlight in a different color. So other than the red part, your IS actually equals to proportional to active area, and then inverse proportional to WBMB. Can anyone tell me what WBMB represents in a physical sense? What does that mean? WB is the width of the base. MB is the doping level of the base. So WBMB represents what? In a physical sense, it's the total amount of dopant in base, right? Because I've doped it with a level MB, and WB is my distance. So that will be the of dopant. I should say acceptor dopants because these are NPN in base. Of course, this is per unit area, per cross-sectional area. So per unit area. Okay? So it means that if you have a wider space, or if you have a higher base doping, it will then affect the IS. So typically, if I want to raise, aside from having a cross-sectional area which allow us to modulate IS, if you're a device engineer, what you want is that you want a lighter base and narrower base, which would then increase your IS. Right? How does one increase IS? Think about it. So to increase IS, so anytime, if you are an engineer going out into a design your own bipolar junction transistors. So you give your boss that I can give you an IS. Typically, area is independent, so it will be a JS, for example. So to increase IS divided by AE, because this is per unit area current, right? So to how does one increase this? First, you lighter dope. Second, you do a narrow base. Okay? Lighter base doping and narrower base. So then your classmate will do the same thing, and then he will then have a better IS, right, per unit area. But of course, there's trade-offs. We're going to talk about trade-offs later. But just give you a sense as to these are the questions that will come in quiz 3, for example. I will ask you that if I compare two bipolar junction transistors, one with a narrow base, the other with a wider base, which one will have a bigger IS, for example, that sort of thing. So you need to know the direction in terms of engineering. But if you look at this is very unique, is that collector current depends on base structure. Okay, so this is very important. When you engineer your base structure, for example, the base width, the total amount of dopant inside base is actually modulating your collector current, because the collector current is coming from whatever is being fed into the depletion region. Okay? This is good? So we're going to talk about a more complicated problem is that, so what about the base current? So once we already know our collector current is the main current that we want to control. And base current is like the price you pay for making the transistor in active mode, for example. So it's like how much you need to pay to turn on the transistor. So base is the part that we actually don't want it to be function because it does not contribute to output current, but it's the price you pay. So we need to talk about how do you make your CP value of your transistor as high as possible. So cost, what is it? Cost price index? CP value, right? So CP ratio. So C is the cost and the cost and performance. Yes, cost and performance. So you want to have the maximum performance, which is IS, and the minimum cost. So minimum cost is the base current. It's the input terminal. Because base is my input terminal, so I need to know how much I need to pay in order to get this collector current. So we're going to talk about base current. So as I already highlighted here, a bipolar junction transistor functions as a current splitter. It will split the electron current and the hole current. And the hole current will be coming in from the base and then flow into emitter. So the emitter diffusion itself will then limit the amount of hole current. So this will determine the amount of hole current. So we're going to do the same exercise on the emitter side. So this is like separating the discussion of 4-bias p-n junction. You discuss the electron and discuss the hole. So the hole current we look at. So what about so in a NPN transistor, let me emphasize again, in an NPN transistor, the IB will be considered, typically will be hole 1 plus hole 2. Let me explain why. In a real discussion, it will be something more like this. So this is NPN. So remember I have electrons here. This is the main current that will contribute to electron current and then becomes the collector current. And then I have you can see that I deliberately make a difference. So I will then have a hole current diffuse into here. So this is IH1, and there's the IH2. So if you have base current coming in, this is total base current. There will be IH1 going to the emitter, and there will IH2 going to the base itself. Okay? So IH1 is to supply diffusion, hole diffusion in base, in emitters. Okay? Now what is IH2? IH2 is recombination. Recombination is that because I have excess amount of minority carrier, the red part, so then there's higher recombination rate. So anytime when you recombine, electron holes need to recombine. Therefore, you have to provide holes for the recombination to happen. But if typically we're assuming that in a narrow base device, currently, most of the bipolar junction transistor, if you want to operate in a relatively high frequency, we're going to talk about frequency dependency later, but the basis needs to be fairly narrow. So for narrow base transistors, we could IH2 can be ignored. Because the transition area is very small, so there's chances of recombination is fairly low. So we can actually ignore this for now. So you can assume that it's close to 0 if it's a narrow base structure. So then your hole current or the base current will then be limited by the diffusion in emitter. Right, let me highlight again. This is emitter base. Okay? So does anyone know why there's a large offset in my drawing in terms of the minority carrier concentration? Why do I assume that? Why do I assume that the minority carrier concentration inside emitter is much, much lower than, why is the blue much, much lower than the red? Why? How does one make that possible? By what? How does you control the minority carrier concentration? You start with, because the forward bias p-n junction will raise the both sides by a same factor, because I'm forward bias p-n junction, right? So the raising ratio is the same. So what the way that by controlling the two is by what? Controlling what? I hear something. Doping. Yes, correct. So remember what happened is that I deliberately made, when we talk about device structure, we deliberately made this Ne, this N plus. We make it NB, this P, and this NC is typically light, right? So you already make that decision of making, in most cases, we want to engineer so that Ne is much, much larger than NB, so that I could reduce my cost. Cost is this base current. So let's look at how does one define base current. So your base current is IB, we'll only consider IH1, so which is the whole diffusion current inside emitter. So the current is going to that direction is the same as current going into the base. So that will be minus Q dP dP dx. Okay? So dP dx is inside, let me emphasize again, this is the profile inside emitter. So as I said, it's very tricky in a way that your collector current depends on the base. Your base current depends on emitter. Okay, so if I want to modulate emitter current, base current, I need to redesign my emitter. If I want to modulate collector current, I need to engineer my base. So it's very, very sort of not that very straightforward, but to get a sense as to where it goes and then what are the limiting components. Okay, so whatever happens inside emitter will determine your base current. So let's take a look at how does one derive this. This is minus Q dP because it's whole current. So what is the profile along this direction is the current's going, you will get a minus sign anyway because the current's going the minus x direction. But anyway, so if you want to create this, we know that at this point, this is MP. MP at x close to 0 again. So this, sorry, it's not MP, it's Pn. So I have Pn. Sorry. So this is Pn at x close to 0, because I'm assuming that the junction is very narrow. Depletion is very narrow. And then we want to talk about this Pn at minus WE. So WE is actually this. Just make sure that it's not confusing. Emitter. So the distance from here to here is defined as WE. So at minus WE. Emitter depth. If you go back to our structure, this will actually means this. So remember, I have collector N, AP, and an N plus, right? So the junction sometimes is referred to as the junction depth. So this would then define WE. The distance between two junctions would define WB. We seldom consider or care about WC because it doesn't really affect the key parameters. But these two will affect our key parameters. Let me try to continue our discussion until maybe 25 past 11 so that you can have 5-minute break before quiz, okay? Good? Okay, so let's wrap up this discussion. So once you have this structure, then we want to define these 2 points. So I know that the distance that for diffusion is WE, right? And at this location is Pn at 0 minus Pn at minus WE. We're following the definition of gradients. Therefore, you start with the left side and the right side. So left, right, left, right. Okay? So then this is JP. I should use JP because I didn't include the area yet. So this will be minus Q dP. So what is on the 0 side? It's 4 bias PN junction, therefore, is PN0 exponential VBE minus VT. So whatever is at this junction, this is typically the metal contact junction. So the surface junction, we're assuming that anytime when you arrive at the surface junction, it will be close to equilibrium state. So at this point, we're assuming that it's PN0. There's all sorts of refinement, but it doesn't really affect our final results because we know that PN0 is very low. So you could simply ignore that. So we simply ignore this for this calculation, and this will be approximately minus Q dP WE Ni square Ne. Let me write it down. So we know that Pn0, this is the minority carrier concentration at emitter during equilibrium, at equilibrium. Right? So Pn0 will be Ni squared divided by its doping concentration. Okay? So then my voltage-dependent term would be exponential VBE. I would take out the voltage-dependent term and take out this minus 1. Doesn't really affect too much. So finally, I can get my base current. The base current will be the minus sign simply because my current is going to the minus x direction. So this is just to take care of the minus x current direction times the area. The area is still the same. The active area is emitter area. So then I would then have a final current equation will be Q dP Ni square WE Ne. This will be whatever is the constant component, and then you have the voltage-dependent component, exponential. Okay? Good? So the next thing is that anytime you do CP value, right? So you want to look at performance, which is our collector current. That's what you want to deliver. And the price you pay at the input, because base is my input. So typically we want to see how much this, if I'm using this device, how valuable or how much gain do I obtain by having the structure. So one of the key parameters for this device is called the current gain. You want to value or evaluate this device by looking at its current gain. So what is the current gain by definition? So there's typically two very important parameters in describing a bipolar junction transistor. One is IS, which will be given to you if I'm using exponential model. So this is like the dial. I'm going to give you IS. The other thing is that we're going to give you current gain. So current gain is another very important spec in describing a bipolar junction transistor. So you look at the current gain, it will be the definition of current gain is beta in this case. The key important typically is referred to as, or sometimes referred to as common the reason why for that will be explained when we talk about transistor or amplifier structures. Another name you can, beta. The current gain beta is sometimes referred to as the common emitter current gain. The reason for that we'll explain later when we talk about amplifier structures. So how does one define beta? Beta is defined as the current ratio between the performance and the price you pay. So base is typically referred to as the price to pay is because in a common emitter structure, that's the input node. So how much do you put in to the system? And this is the output terminal. So in a common emitter structure, this typically is the output. Not always, but in this structure, this is the input. So how much you put in, and then you gain enough for, so how much you put in, and then the ultimate performance is IC. So let's put our equation in. So I need the whole thing so that we can get the complete results. I have 15 more minutes. Yeah, we can get that. So let me write this whole equation in yellow, IC, which is AE QDM. Make sure that I don't miss anything. So you keep an eye for me. WB NB. Exponential VBE. This is IC, and the bottom is, the reason why I'm writing the whole thing is because the top and bottom cancel itself a lot. So on this side, I'm also given the IE Q dP NI square W E N E. Okay? So exponential VBE. So if you look at the collector current and the base current, it both raises exponentially with VBE. So it has the same voltage dependency. It's the same active area, the same voltage dependency, and the same, not the same constant because different type of carrier. So diffusion constant, diffusion coefficients are different, and NI squared. Okay? So then you get a very clear vision as to what to do to get a better gain. Okay? So it will be N, E, W, E, N, B. So we're going to put them into ratio because these are the same type of things. let me separate them. So what you do is that it depends on doping ratios between the two, emitter and base. And then it depends on the depth of junctions or distance between junctions, ratio between the two. And then it depends on D and dP. And this also depends on, if I want to rewrite this, this also depends on, because it's a constant at the same temperature, so it would directly depend on mobility ratio. Okay? So if you will come into this conclusion as to your overall, well, let me rewrite it here. So your beta, let me summarize it. Beta would depend on ratio between and then finally mu n, mu p. Okay? So if you look at in an engineering point of view, what can be manipulated most? Do I have a lot of room in engineering the base and emitter width? I make a base very narrow, but the depth very WE. So how do I make this ratio high? Or is it possible to make it high? In typical, this is the ideal characteristic. So if I'm making it whatever using the building blocks, I can actually make my emitter as wide as possible. But in this case, because we know that the emitters are built in terms of in integrated circuit technology, the emitters are built at last. Therefore, it's typically the junction depth is typically very hard to engineer. Therefore, this thickness is typically the thinnest, or at most, these will be comparable. So in real practice, what happens is that this will be mostly close to 1, meaning that it's comparable level. Even though there's smaller difference, it's very hard for you to create large emitter depth and smaller WB at the same time. So that in most cases, these are keep fairly in a comparable level, meaning that the ratio is close to 1. And typically it's being done is this. Remember, this is M plus. This is P. So what we typically want to do is to make NE much, much larger than NB. So typical range will be somewhere like this is 10 to the 19th, and this will be 10 to the 17th. So then you can create a ratio simply by suppressing whole minority carrier concentration emitter by heavily doped. So that is the reason why we have heavily doped emitter in order to have high gain. Otherwise, your gain will be very poor. So this would then create over 100. And then, of course, this is non-controllable. So this is whatever it's being given. So the ratio is about 2 to 3. So then overall, you will see bipolar junction transistor will have a beta somewhere around, for NPN transistor, typical beta for NPN is approximately 100 to 200. If you don't do very special design, then 100 to 200 is the typical number of having a current gain of, for a bipolar junction transistor, simply by manipulating the doping concentration between the two. Okay? So this will then give you, I would like to give you 2 questions to think about when you take it, after you take the quiz. Of course, don't want to disturb you on that. So one is that I highlighted that this is for the NPN transistor. You can actually do the exercise on the PNP side. We're probably going to have some time to talk about that a little bit. But just to look at this equation, if you think about it, if I'm having the same structure, the same doping level, it just becomes P plus N. and then the same base dimension, base emitter ratio dimension ratio. And what do you expect the beta will be? So if the structure is the same, it just becomes PNP. For example, if I'm building the same thing, so the question is, if I'm building a PNP, so for example, this will be a P. You might need to have a well, but it doesn't really matter. N well to isolate from the ground. But if I'm building the same thing with P and P, so it has the same WE, same WB. The counterpart, this will be your PNP. With the same doping concentration, for example, let's say if this is 10 to the, let me just give a raw number. This is 16, this is, as I said, 17, this is 19. So it's the same 16, 17, 19. Okay? So for NPN and PNP transistor, which will have a larger gain? Just to pick. Which one would you use? I already hear the answer. Why? Why? Why do you think that NPN will have a higher? You'll see that in the class, if you go to the next chapter, you'll see that all our circuits, you don't see PNP. There must be a reason why, if it's better, why don't you use it? It's worse, because it depends on the ratio. And if you think about it, why is it depends on the ratio? This is because my main current that I'm delivering is electron current. Collector current is electron current for NPN. For NPN, the whole current, the base current is whole current. Therefore, you use these two ratios. If I'm doing PNP transistor, what happens is that my main current will be whole current, and the base current will be electron current. So that it will reverse the type, so your ratio will be counter, it will be 1/3. So you actually degrade the gain by 4 times to 9 times. Meaning that for the same structure, if I'm getting 100, the other will be 25. Okay? You can go back and think about it. It's just a math problem. It's a square thing. Okay? So you counter it with a ratio. Therefore, it would further degrade. But if you don't look at the number, the basic idea is that if I'm having an NPN transistor, my main current is electron current. Electron moves faster. For PNP transistor, my main current is whole current. Whole current moves slower. So the cost I'm putting in is electron current. So I'm paying more to get the same performance. Okay? Is that helpful? So I think I'll stop here and give you some break time before the quiz. So if you have any question, we can still, I'll still be here before the quiz is delivered.